Physics chapter 23, theory video 2. We are going to discuss about energy stored in a capacitor. Now we learnt earlier that when we charge a capacitor, what happens is electrons are pushed onto one plate, and that results in the electrons being pushed out of the other plate. So there is work being done on these electrons by the power. So as a result, potential energy of these would increase. So this increase in potential energy is what we recover after when discharging the capacitor. So when we charge a large capacitor, something like 1000 microfarads or more, to a potential difference of 6 volts, and if we connect it across a 6-volt lamp, then we can see the lamp glowing, but that flash is not going to last long. It will quickly vanish. That is because the energy that is contained, or it does not store that much of energy. It is only for the functioning of that small circuit. That is what that is we don't store too much of energy. It is just a small tiny little bit of energy that is stored in here. So then when work is being done to push these electrons onto one plate and of the other, we need to do work. So this work is done by the power supply. Now when at the beginning stages, the amount of work that needs to be done is quite small, because there would be much less repulsion because of the electrons. However, when we increase the charge on the plate, there is more and more work that needs to be done. You can understand why that is, because obviously when the negative charges increase, more and more negative electrons get stored here. As a result, more and more repulsion would be there. So to overcome this repulsion, we need to make sure that that more work needs to be done. So as a result, there is a higher amount of potential energy that would get stored. Now in this figure, we can see how the electrons are repelled and attracted how electrons are deposited, and as a result, electrons are pushed out of it because of the pushing. Here there is a pushing effect, so as a result there is a pulling effect here, and that results in the entire system to get charged. Now if we look at 23.7a graph here, this is in this graph we can actually see qualitatively how the potential difference voltage increases as the charge increases. Because it is a straight line, we know that V is equal to Q upon C. That relationship also you must understand. So these equations you have to not only remember but also understand how they are brought about. Now in the same equation, so the voltage and Q, this is the energy stored. The purple part shows us the energy that is being stored. So the work done in moving charge Q through constant PdV is given by W is equal to QV. W equals QV. So the QV is given by the area under the graph, but because now here in this one the shaded region is a triangle, so that is, you can, as you can see, it is half Q into V because it's a triangle. Then the work done in charging a capacitor to a particular PD is given by W equals half QV, right? So now we learned earlier that when work done when moving a Q through a constant potential difference of V, the work done would be W equals QV, right? So we now understand that the work done when charging a capacitor is W equals half QV because it is a triangle. Then if we substitute this relationship Q equals CV from this equation, Q equals CV, then we will see that W is equal to half CV squared, or W equals half Q squared upon C, right? So that relationship also can be taken into consideration. Right, so you can see that energy required to move a charge of Q through a potential difference of V is this, but for a capacitor it is going to be this. Now, in these examples, the W is energy stored, Q is the charge on the capacitor, C is the capacitance. Please don't misunderstand it with coulombs, and V is the potential difference across the capacitor. So when work is being done when charging a capacitor, that work being done is equal to the amount of energy stored in the capacitor, because that is the amount of energy that would be released when the capacitor does work. So in the second formula, W equals half CV squared, we understand that the energy W is the amount of energy that would be stored when this voltage of V flows through this. So then we can understand that W is going to be dependent on capacitance C and the potential difference V, because W is proportional to the square of the potential difference, that is, W is proportional to V squared. That means if we double the voltage, 4 times the energy would be produced. I suppose you understood that, because W here is proportional to V squared. W is V squared. So as a result, when the voltage is increased, we get double, 4 times the energy would be stored. So these equations you must remember: W equals half QV, W equals half CV squared, and W equals half Q squared upon 2C, or else half into Q squared upon C. So let's go through this worked example, then you will be able to understand how these questions are done. A 2000 microfarad capacitor is charged to a PD of 10 volts. Calculate the energy stored by the capacitor. So we write down the quantities that we know, then from that we can find out which equation to use. They have given here the capacitance 2000 microfarads. So C is 2000 microfarads. Then V they have given to be 10 volts. Then what is the equation we need to use? Half CV squared. So when we do that, it is going to be 0.10 joules. Now if you take here from this one, we can understand why it is such a small charge. Because if you take a rechargeable battery, it would have 10,000 joules of energy in it. So a charge capacitor cannot make a mobile phone. If your mobile phone lost power or a computer lost power, the computer cannot be functioned by this, but the internal circuits or else the memory part might work for 1 or 2 seconds until all the documents are saved. So that is how these capacitors work. I would suggest that you do question number 5 and 6. After you have written the note. Write down the note. A capacitor does not store much energy and it cannot provide a lot of energy when it is discharged. When charging the capacitor, initially only a little amount of work needs to be done because the repulsion of the electrons is lesser. However, when the charge builds up, more and more work needs to be done, and as a result, there would be more energy being stored. Leave a line and write. When a charge Q is driven through a potential difference of V, the work done is shown by below graph, and please draw this graph. However, after drawing, write this down. However, the amount of energy stored when the same charge is moved through potential difference of V, only half that energy would be stored. below three equations can be used when calculating energy released when the capacitor is discharged. And write down these three equations. W equals half QV, W equals half CV squared, W equals half Q squared upon C. Then write down what W stands for. W is the energy stored, Q is the charge, V is the potential difference, and C is the capacitance. I hope you understood. If you have any questions, please raise them.